Disclaimer: this presentation is created for educational and informational purposes only. All company names, products, and trademarks mentioned are the property of their respective owners and are used here for reference or illustrative purposes only. The information presented is based on publicly available sources, industry reports, and reasonable assumptions as of the date of recording. While care has been taken to ensure accuracy, no guarantees or warranties are made regarding completeness or correctness. This content does not represent any official statement, endorsement, or affiliation with any company or organization mentioned.
Welcome everyone. Today we are going to explore inside the brain of the software defined vehicle. How modern cars are evolving from machines with electronics into software defined intelligent systems. This is part 3 of our SDV series, where we'll dive into architecture, compute platforms, and cloud integration, the very foundation that makes smart, connected, and autonomous driving possible. So, here is our roadmap for today. We'll begin with how vehicle architectures have evolved from traditional distributed ECUs to fully centralized compute. Then we'll explore the compute and hardware platforms that power today's autonomous systems. We will talk about the software stack and middleware that makes these cars truly programmable. And finally, we'll close with cloud integration, OTA updates, and the role of connectivity. By the end, you will see that the modern car is less of a mechanical device and more like a rolling data center. Little bit about me. My name is Prashant Prabodh and I have almost 25 years of experience. I have worked in banking and finance domain, automotive. Last couple of years I've spent in GenAI healthcare, and otherwise I've worked in embedded systems, IoT, and semiconductor consumer electronics. Past almost 14-15 years I've spent into architecture and design, mostly SOA and microservices based architecture for distributed systems and few of the cloud services as well. Uh, Programming, I have spent tremendous amount of time on modern C++, C++11, 14, and recently I've started with Python, Fast API, and reactive and functional programming. Yeah, that's it about me. The evolution of EE architecture. If we look at the past 3 decades, automotive electronics have gone through 4 major architectural eras. From 1990s to 2010, we had distributed ECU systems. Each function, whether it is ABS, airbags, infotainment, and wipers, uh, had its own electronic control unit, or ECU in short. These were all connected through CAN or LIN buses. Around 2010, we started grouping ECUs into domains like body, powertrain, ADAS to simplify the communication. By 2018, that shifted into zonal architectures, where instead of functions, ECUs were organized by physical location, front, rear, cabin, and from 2023 onwards, we are entering into the centralized or software defined era where a few powerful computers, often called as HPCs, high performing computing, or vehicle brains, manage the entire car. So we have moved from hardware controlled vehicles to software defined intelligence, very similar to how computers evolved from desktops to cloud computing. In the early 2000s, a premium car easily had over 100 plus ECUs, each running its own firmware. All that wiring added up to around 60 kilograms of copper. That's a cost of roughly $1,000 per car just in wiring. Each ECU was isolated. Your infotainment couldn't talk directly to your ADAS or your braking system. So, software was proprietary, updates required physical visits to workshops, and integration was extremely complex. Think of it like a company where every department uses its own mail system. No shared data, no collaboration. That was the automotive world before the domain and zonal architectures. The next step was the domain based model. Here, issues were consolidated under domain controllers. So, all the powerful functions were managed together, the ADAS systems together, and so on. This brought down the ECU count over 100 to about 30 to 50, and wiring became a little cleaner. Software integration within a single domain was much easier. For example, coordinating the braking and the stability control within the same controller. However, the cross domain features were still challenging. For instance, adaptive cruise control needs data from both the ADAS and powertrain domains, and that required complex bridging logic. So, it's solved part of the problem, but the systems were still not truly unified.
Then came the zonal approach. Here, the idea was, let's organize compute units not by functions but by physical location, front, rear, cabin, and so on. Each zone manages the local sensors and actuators nearby, while the central backbone connects them through a high speed Ethernet. This approach cut down wiring by 30 to 40%, saving weight, cost, and manufacturing effort. Remember, every 10 kilograms you save gives you roughly zero point 0.1 kilometer per more range in an electric vehicle. Diagnostics became easier too. If there is a sensor issue in a rear zone, the system shows and knows exactly where to look. The trade off, of course, is that this demands a powerful central compute and a very fast deterministic network. In a way, it's like organizing a city into local districts that all report to the central tower control unit. Now, we are in the centralized compute era, the brain of the software defined vehicle. Here, most functions run on one or two high performance computers, supported by zonal controllers, acting as a smart gateways. These HPCs host virtualized environments, running everything from ADAS to infotainment to vehicle control. They use AI accelerators, GPUs, and multi-core CPUs to process sensor data in real time. Examples include Tesla FSD computer capable of around 1144 trillion operations per second that stops. NVIDIA Drive Thor takes it to the next level, offering up to 2000 TOPS in a single SoC. And Qualcomm's Snapdragon Ride Flex is designed to handle both safety critical and non critical workloads simultaneously. You can think of this as the car becoming a mini data center where hardware resources are dynamically shared across multiple services. Compute requirements by autonomy level. Now let's look at something every software defined vehicle depends on: compute power. Think of it as the brain capacity of a car. The higher the number level of autonomy, the bigger and faster this brain needs to be. At level 1, The car is doing small bits of assistance, things like basic control or lane departure alerts. These systems need anywhere from 10 to 100 tops. That's trillion of operations per second. It sounds huge, but by AI standards, it's quite lightweight. About what a mid-range laptop GPU can do today. Okay, when we step up to level 2, we enter the realm of partial automation. This includes adaptive cruise control, lane centering, and basic traffic jam assist. Here, you are looking at around 200 to 400 tops, roughly that NVIDIA Orin or Qualcomm Ride platforms deliver today. This is where the vehicle begins to understand its environment using multiple sensors like cameras, radar, and sometimes even LiDAR. Level 3 autonomy. Level 3 autonomy means the car can handle full driving in certain conditions, say highway driving, but still expects a human to take over occasionally. This needs a serious jump, around 600 to 1000 tops. Systems like those used by Mercedes or Honda's Level 3 vehicle are already in this range. Then we hit level 4, where robotaxis like Waymo or WeRide operate. These cars are practically self driving in specific geofenced areas and they need roughly 1000 to 2000 tops. At this level, we are running multiple deep learning models in real time perception, localization, motion planning, all simultaneously. Finally, level 5 is the holy grail full autonomy. No steering wheel, no pedals. Here, we are talking about a staggering 2000 to 4000 tops. That's the equivalent of having several and high-end gaming GPUs running together inside one vehicle, all under strict power and thermal limits. To put that in perspective, some test fleets today generate 3 to 4 terabytes of sensor data per hour. That's like streaming over 500 Netflix 4K movies every single hour just from the car's sensors. And the vehicle's onboard computer has to process all that in real time, make split second decisions, and do it safely without overheating or drawing too much of battery power. In short, as cars get smarter, their brains grow exponentially more powerful. Each jump in autonomy roughly doubles or triples the compute demand. And that's why we are seeing such a boom in specialized automotive AI chips and accelerators. Hardware and compute platform. The modern SDV compute stack includes several types of silicon. We have CPUs, typically ARM and RISC-V, handling control logic. GPUs take care of vision processing and rendering. NPUs or AI accelerators handle deep learning workloads. Then there are safety islands, small microcontrollers that monitor for fault and ensure fail operational behavior, and high speed NVMe SSDs to log terabytes of sensor data. But with great power comes great heat. These chips can produce 200 to 300 watts of thermal load. That's equivalent to several laptops running at once. And they must be cooled efficiently inside a sealed automotive environment. All this must also meet automotive grade reliability standards like AEC Q100 with lifetimes of 10 to 15 years. Real world compute platforms. Some real world examples of these platforms include NVIDIA Drive Thor, up to 2000 TOPS, capable of unifying all domains from perception to infotainment on a single chip. Qualcomm Ride Flex, which blends real time safety with entertainment workloads. Renesas R Car, used across ADAS and gateway systems in mainstream vehicles. Tesla Dojo, which isn't inside the car but in the cloud. It trains Tesla's neural networks using fleet data. And WeRide, in partnership with Lenovo, uses redundant edge compute nodes for their autonomous robotaxis. The key takeaway: compute now extends from car to cloud, forming one continuous AI ecosystem. SDV software stack overview. The software stack of a modern vehicle looks a lot like cloud system. At the base we have hardware, MCUs, SoCs and sensors. Above that sits the OS layer, QNX, Linux or AUTOSAR adaptive. Then comes middleware, DDS, some IP or ROS2, enabling the consistent communication between the systems. Next, we have the service layer, a vehicle OS, exposing standardized APIs. And finally, the application layer, ADAS, infotainment, telematics, fleet management. The key idea here is hardware agnostic software. Just like Android allows different phone manufacturers to run some same applications, SDVs aim to make car software portable across different hardware platforms. Service oriented architecture. In a service oriented design, every function like steering, assist, braking, or parking is exposed as a callable service. That means developers can build, test, and update those services independently, even over the air. It's a huge step forward in modularity and maintainability. You can add new capabilities through software, much like installing an app on your phone. BMW already does this. Customers can unlock new features like heated seats or adaptive lights just through an OTA update. Organizations like Covisa and SDV Alliance are now defining open API so these services can work across different OEMs. This is what makes cars software defined, not just software enabled. To connect all these services, middleware plays a vital role. We have some IP for service communications, DDS for real time publish subscribe messaging, and ROS2 for ADAS and robotics applications. On top of that, virtualization allows multiple environments to run on the same hardware. For instance, a QNX real-time OS for braking and a Linux system for infotainment, both safely isolated through a hypervisor. It's just like running multiple virtual machines or a Docker containers on your laptop, isolated but sharing the same hardware efficiency. Over the air updates are one of the biggest enablers of the SDV concept. OTA systems allow both firmware and software to be updated remotely, securely, and without visiting the service center. They use Delta updates to minimize data transfer, rollback mechanisms in case something goes wrong, and secure boot verification to ensure integrity. Platforms like AWS IoT FleetWise, Azure IoT Hub, and Bosch Vehicle Cloud are leading in this space. Tesla, for example, has pushed hundreds of updates to its vehicles, sometimes adding new features overnight. This is where the car starts behaving more like a smartphone, constantly improving over it leaves the factory. The car, the edge, and the cloud are now deeply connected. Here is how it works. The vehicle collects data, sends it to Edge Gateway. That data is filtered and sent to OEM cloud, stored in a data lake, used for retraining AI models, and back updates come back OTA to the fleet. This enables digital twins, virtual replicas of each car running in the cloud for simulation, for diagnostics, and predictive maintenance. Examples include AWS's SDV Cloud, Continental's CA Edge, and Microsoft Azure's Connected Vehicle Platform. So now your vehicle isn't just a physical product, it's a node in a continuously learning network. Of course, once you connect cars to the internet, cybersecurity becomes critical. Threats include intrusion through OTA or infotainment systems, and even data theft through APIs. Defense starts at the hardware level, using secure boot, hardware security modules, encryption, and intrusion detection within zonal controllers. Automakers also need to comply with standards like ISO 21434 for cybersecurity engineering and UNECE WP.29 R155 for regulatory compliance. Think of it like your car having both a firewall and antivirus, but built into silicon. Connectivity is what ties all this together. With 5G NR and cellular vehicle to everything, C2 V2X vehicles can communicate with each other and with infrastructure in real time with latency under 10 milliseconds. We also see Wi Fi 6 and satellite links as backup channels. Use cases include cooperative perceptions, cars sharing camera or radar data to see around corners, real time traffic coordination, and smart city integration. In trials by Audi and Qualcomm, CV2X reduced intersection collisions by up to 40%. So, connectivity is not just convenience, it's safety. AI and foundational models. The next wave is the rise of foundation models for driving. Large multimodal AI models that can understand camera, radar, LiDAR, and map data together. These are like GPT style models but trained for perception and decision making on the road. They can reason about context, predicting what other drivers or pedestrians might do, not just react. Companies like WeRide are already retraining their fleet models every 2 weeks using real world telemetry. This enables more human like decision making, personalization, and predictive maintenance. Your car will know something's off before you do. The software defined vehicle also needs a strong developer ecosystem. This includes SDKs and APIs from companies like NVIDIA, uh, Cariad, and the SDV Alliance. Simulation tools like Carla or IPG CarMaker help test algorithms safely before they ever reach a real car. And CI/CD pipelines automate OTA deployment, while DevSecOps ensures cybersecurity throughout the development lifecycle. In short, we are moving from traditional automotive engineering to continuous software delivery, just like modern cloud development. Of course, this transition isn't easy. Engineers face constant trade offs: deterministic behavior versus software agility, computer power versus battery efficiency. We still have to migrate legacy ECU code bases that were never meant to run in virtualized environments. And validating AI decision layers under safety certification is a massive challenge. So, the need of an R is a unified development life cycle that allows both innovation and guaranteed safety. Let's see how global OEMs are approaching this. Tesla is fully centralized, with its Dojo training platform feeding its full self driving stack. BMW follows a zonal plus SOA strategy based on AutoSAR adaptive. Toyota takes a hybrid domain zonal route using QNX and custom middleware. Volvo and Polestar use Android Vehicle OS integrating directly with Google's automotive services. And Volkswagen's Cariad is developing VW.OS, a common software platform across multiple brands. Each OEM is balancing differently between control, openness, and scalability. And that brings us to the end of today's session. In the next part, we'll look at the challenges and future roadmap for SDVs. Things like AI safety, scalability, and open developer ecosystems. Remember, the shift to software defined vehicle is not just an evolution of technology, it's a cultural shift in how cars are designed, built, and continuously improved. Software is no longer a component, it's the soul of the modern vehicle.